All right, guys, welcome to Chapter 8. So Chapter 8 is going to be solution chemistry. So now what we're going to do is we're going to start to look at the properties of a solution, and then we're going to look at the different types of molecules in a solution. So now we know a little bit more about each type of molecule. We can see how it reacts in a solution and then how that changes the properties of that solution. So first, let's just talk about the definitions that we're going to be using in this chapter. So a solution is a homogeneous or homogeneous mixture of two or more substances. So remember that word homogeneous or homogeneous means it's uniform throughout. So you can't tell where one thing starts and stops. It just looks the same from top to bottom. So two or more substances. Those two or more substances are going to be given a title now. So the substance that's in greatest proportion is going to be our solvent. So a classic example of a solution would be like the ocean water or salt water. So in that case, the solvent would be the water, H2O. That's in the greatest proportion. The solute are all of the other substances in lesser proportions. The solute can be any number of things, so it can be more than one. So if we use our example of ocean water or salt water, it could be the salt that's dissolved in water. It could be the oxygen, nitrogen dissolved. It could be the fish poop. It could be anything we wanted it to be inside of that solution. So solvent, one singular thing in greatest proportion. Solute, could be multiple other things in lesser proportions. If we're talking about the solutes that are in that solution, we could classify them in two different categories. So a dilute solution would be something that has a very small amount of the solute compared to solvent. And then that is in contrast to a concentrated solution. So a concentrated solution is going to have a large amount of solute compared to solvent. So to drive this point home, the analogy I always use is sweet tea. So sweet tea in the north versus sweet tea in the south. Sweet tea in the north would be a dilute solution. So let's say the solvent is tea, and then the solute is the sugar that's dissolved in that tea. In the north, we would have lots and lots of tea, and we'd put just a little bit of sugar in there, right? Dilute solution. When you're in the south, you would have the same amount of tea, so lots and lots of tea, but you would add lots and lots of sugar to that tea, right? So sweet tea in the south is a concentrated solution. So lots and lots of solute compared to solvent. So that's the difference between dilute and concentrated. There's lots of units for the concentration of solutions that you will come across in science. You might have heard of things like parts per million, parts per billion, percentages, things like that. But the unit for concentration that we're going to use in chemistry is something known as molarity. So we love the mole in chemistry, right? It's our best friend. So we're going to use the the unit molarity. Molarity is the amount of solute in moles, because we're chemists, divided by the volume of solution, and the unit we're going to use for volume is liters. So moles of solute per liters of solution. So here is your unofficial formula for molarity. And then this is how it would be written kind of in shorthand using the variables. So we use a capital M for molarity. V stands for volume. And don't ask me why, but we use the letter N to denote moles. The silly way that I remember this, welcome to Miss Maz's brain, is when I see the letter N, my brain literally says number of moles. So that's how I remember that N stands for moles. So the number of moles. Okay. So let's dive into just a really, really simple plug and chug problem to get to know this. All right, so if you dissolve 25.5 grams of potassium bromide in enough water to make 1.75 liters of solution, what's the molarity of that solution? Okay. So first things first, I see this word molarity. That's what it wants me to solve for. So I'm going to go ahead and get my formula onto the paper. So molarity equals number of moles divided by volume. Then I'm going to organize my thoughts. So I'm going to come over here to the side and I'm going to take inventory. So molarity, number of moles, volume. So what do I know? What am I trying to solve for? Okay. Well, here it says, what is the molarity? So this must be what I'm solving for. So I must have the other two variables somewhere. Okay. So I see this 1.75 liters. So that 1.75 liters is the volume. So 1.75 liters. Now I just need to read through the problem and find moles. Does it say how many moles of potassium bromide we used? No. What does it give us? It gives us grams, right? And this is something indicative of being in a lab. So you wouldn't walk over to a scale and weigh out the number of moles, right? You'd walk over to the scale and weigh it out in grams. Do we know how to get from grams to moles? Yeah, we're experts at that, right? By now. So the first thing we're going to have to do is go do a unit conversion from grams of KBr to moles of KBr because that's what I need for my formula. So I'm going to take 25.5 grams of KBr, set up my train tracks. Grams is going to go on the bottom or diagonal because that's what I'm getting rid of. And my formula needs moles of KBr, so that's my destination. That's what goes on the top. So how do we determine the number of moles of KBr? Well, remember, we use the molar mass. So in 1 mole, and then we go to our periodic table to get the molar mass of KBr. So potassium is 39.098 plus bromine, which is 79.904. So add those two together, and the molar mass for potassium bromide is 119.002. Okay. So multiply across the top, divide by the bottom. So I'm going to take 25.5 divided, or multiplied by 1, divided by 119.002, and I get 0.214 moles of KBr. Okay. So now I have the unit of moles. Now I can put it over here in my inventory. And now I'm ready to rock and roll. I have 2 of the variables. I can use 2 variables to solve for 1. So I'm just going to get rid of this so I have some space to work on my molarity. All right. So now let's plug and chug. Plug it into the equation, chug through it. So molarity equals moles on top, 0.214 moles. Volume on the bottom, 1.75 liters. So divide those two numbers and we get 0.214 divided by 1.75 and we get 0.122. Okay. Units for molarity. So you do have options here. So we can use that capital M. So the way that we would read that is this is a 0.122 molar solution. Or you could explicitly use the units from your problem. So I could also write 0.122 moles per liter. So both of those mean the same thing. Both of those are going to be perfectly acceptable units. You just choose your path. Pick which one you prefer. All right, let's look at one more example. So go ahead and pause the video, see if you can get the right answer, then I'll work through it with you. All right, so how many liters of a 0.125 molar sodium hydroxide solution contains 0.255 moles? All right, so asking for something a little different. It's asking for, gracious. It's asking for liters, okay? So let's get our formula onto the paper. Let's start taking inventory of what we know and what we're trying to solve for. So how many liters? We are solving for volume, okay, of a 0.125 molar. So that's our molarity. And it contains 0.255 moles. So that's our moles. Okay. So now we've got two variables. We need to solve for the last one. Let's plug and chug. So plug it into our equation and chug. So molarity 0.125 molar equals number of moles on top, 0.255 moles. And volume is our unknown that's on the bottom. The reason I put one of these into our lecture series is because this is one of the most missed algebra problems. So you guys do a great job of setting these problems up, but then you make an algebra mistake along the way. So watch how I solve this. The first step in solving this is to get the variable out from under that fraction. So solving for a variable on the bottom of a fraction is really, really difficult. So the first thing I'm going to do is get it out of there. So I'm going to multiply by the reciprocal. That's the technical term for it. But I'm going to multiply this side by v. So v on the bottom, v on the top. They cancel. Whatever I do to the right-hand side, I also have to do to the left-hand side. So I'm also going to multiply this side by v as well. So just simply rearranged. So now what we have is we have 0.125 molar times volume, and that equals 0.255 moles. Okay, so volume is no longer on the bottom of a fraction. So now what we can do to get volume by itself is just simply divide by molarity. So 0.125, that cancels. Whatever I do to the left side, I have to also do to the right side. So divide by 0.125. So we're left with volume on the left, and now we just type that into our calculator. So 0.255 divided by 0.125, and we get 2.04. What are our units? Well, you can just remember that our units are liters, or we can derive the units. So remember, molarity can also be written as moles per liter. So let me explicitly write that out. Okay. Now we can follow our units. So moles on the top, moles on the bottom. We're left with the unit of liters, which is good news because we were solving for volume. Okay. So that is the answer to this problem. So again, I put this in here with the variable being underneath. That's an algebraic mistake I see a lot of students make, so I wanted to just go over that very explicitly with you. Okay. So the last thing that we're going to talk about in this series or in this video is something called dilutions. So we're going to apply the molarity equation to a specific scenario, and that scenario is going to be a dilution scenario. So stock solutions. Stock solutions are what we order in a laboratory setting. So stock solutions are commercially available at very, very high concentrations. So like 12 molar hydrochloric acid. If you put 12 molar hydrochloric acid on any specimen, biological or chemical, it likely would just ruin the specimen, or it'd react so quickly that you couldn't actually observe what was going on. So we can't use these very high concentrations. So what we do as chemistry instructors, or really as science instructors, is we dilute them down. So we lower the concentration of those. So I might take a little bit of that really concentrated stock solution, put it into a volumetric flask, fill that flask up with water, and now the hydrochloric acid that's in this little volumetric flask would be a lot more dilute or less concentrated, and something that we could actually use in the laboratory. So the bottles that you would see in the laboratory that we would actually use would be those diluted solutions. Okay. So here's just another picture of how this dilution process works. So we would take a little bit of our concentrated solution. We would put it into what we call volumetric flasks. So how do I know that this is concentrated? These blue dots represent the solute particles. So lots of solute particles in this little bubble. So I put that concentrated solution into this flask. Then I would fill this flask up with deionized water. And now if I were to peek at this solution, we see that it's dilute. So how do I know it's dilute? I see lots of those solute particles, lots of those blue dots inside of the same sized bubble. Okay, so that's the process of dilution. Now, we can't just blindly take our concentrated solution, throw it into a flask, and then fill it up with water. We want to know exactly what the concentration of these solutions are. So what I'm going to teach you now is the math of these dilutions. So how do we solve for these types of problems? Okay. So here's our problem. Suppose we're preparing a 250 milliliter solution that is 0.01 molar in copper ions. We're starting with a stock solution of 0.1 molar copper ions, and we're trying to solve for, well, how much of that stock solution do we need? What's the original volume that we're going to take out? Okay. The formula for dilutions is the following formula. So the formula we're going to use is M1V1 equals M2V2. So this formula here is actually derived from the molarity equation that we just studied, that we just looked at. So M1 and V1. You might also see this as with lowercase c's here and lowercase d's here, or subscript d's here. So M1 and V1 are going to be the molarity and the volume of our concentrated solution. Okay, so this would be our concentrated side, or our stock solution. M2 and V2 are going to be the molarity and the volume of our diluted solution. So when we're done diluting this down, that would be the molarity and volume. Okay. So what we're going to do now that we have our formula is, again, we're going to organize our thoughts. We're going to take inventory of what we have and try to decide what is it that we're solving for. So let's read through this problem again. Suppose we need to prepare a 250 ml solution. So this word prepare tells me that this is going to be my V2. This is going to be the solution that I make, the diluted solution. So V2 is 250 milliliters. Okay. And that solution is going to be 0.01 molar. So my diluted solution, the concentration is going to be 0.01 molar. Okay. We're going to make this solution by starting with, this is our concentrated or our stock solution. So that's M1. That's the molarity that we're starting with. And at this point, you can always pause and just kind of make sure this makes sense. So concentrated should be a bigger number or higher number than diluted. So 0.1 would be more concentrated than 0.01. So that makes sense. Okay. All right, and we're solving for what is the volume. So this is the variable that we're solving for. So now that we have our formula, now we have inventory, we have one variable that's unknown, we can plug and chug. Plug it into the equation, chug through it. So M1 is 0.1 molar. V1 is what we're trying to solve for, so that's going to remain a variable. M2 is 0.01 molar. And V2 is the 250 milliliters. Okay. Now what we want to do is just a little algebraic rearrangement to solve for V1. So to get V1 by itself, I'm going to divide by 0.1 molar. On top, on bottom, that cancels. Whatever I do to the left side, I also have to do to the right side. So 0.1 molar. So we're left with V2 equals, let's real quick follow our units before we pick up our calculators. So molarity on top, molarity on the bottom, those cancel, and we're left with the units of milliliter. Okay, so now we can pick up our calculator, and we're going to type in 0.01 times 250 divided by 0.1 equals, and the volume is 25 milliliters. Okay. Oops, that's V1, not V2. V1. Okay. So what we just solved for, what in the world did we just solve for? That's a great question. So if I click back to this dilution process, what we just solved for is we are going to take 25 milliliters out of this stock solution. So I'm going to pipe that 25 milliliters out. I'm going to go ahead and put it over here in a 250 milliliter volumetric flask. Okay, so that's taking my concentrated, putting it in here. Then, when I fill up this volumetric flask the rest of the way with deionized water, now I know exactly what the concentration is of this diluted solution. I know that this diluted solution is 0.01 molar. So what we calculated was how much of the concentrated solution we need to take out originally. Okay. In these dilution equations, I could really form these problems where I could ask for any of the variables. So be prepared for that. But what you're going to want to look for to recognize that it's a dilution problem is I will likely use the word dilute. So I would say something like, I want to dilute a 0.1 molar solution down to 0.01 molar. So if you see the word dilute, that should be a good indication it's a dilution problem. The other thing you'll see is different molarities. So here I see 0.01 and a 0.1. So with these two different molarities, likely going to be a dilution problem. So how do we get from one to the other? So just some red flags. We've got lots of formulas in this chapter. So just some red flags to help you identify a dilution problem. So I think that's it. Yep, that's it for this video. I hope you guys found this helpful.